Okay, good morning, everyone. As you have seen, I've set up some, I gave you links to examples of midterms from previous years. So we have quite a big library of exams and midterms. So you're welcome to use it for preparation. So that all the instructors that I know of, they used Stewart's book for this course, and I think it's department, it's accepted over the department. So yeah, those problems that you saw in this database, they are quite representative of what you expect, what you expect for the midterm and the final. Yeah. And then, as I promised last time, I haven't done it yet, so I think I'm just going to set up a website where I'll just put links to all videos that we had, because by now we have many, with a short description of what was done in each video, and I'll just put all the PDF notes, iPad notes to the lectures that we have. Any questions? So tomorrow we have a review, and then there will be also office hours as usual at 2. So you're welcome to bring your questions. On Thursday we'll have a quiz, so there will be no lecture on Thursday. We'll just have I think we'll set up a 24-hour window between 10 a.m. Thursday and 10 a.m. on and I'm doing a lecture. Ask mommy. Yeah, sure.
Я хочу мышь.
Just 1 second. Олесик, у меня лекция. Олесик, у меня лекция сегодня. No, Anna, I need the iPad. Anna, Олесик, у меня лекция. I'm sorry for that. My daughter watches cartoons from my iPad. Thank you. Yeah. Yeah. So yeah, as one of my colleagues joked that we all have become elementary school teachers. Well, she's not in school yet. Yeah, so like what COVID brought to us, that we all know how to teach elementary school now. Yeah. Anyhow, so right. Yeah, I hope it's pretty straightforward. Good. So the Lagrange multipliers are used to it's a very useful tool to solve optimization problems. So say you have a rectangle, right? And then you asked with whose sides length are A and B, right? And then you need to find the maximum area for a fixed perimeter. So say you know the perimeter, which is 2A plus 2B, is fixed. And then you need to find what is the maximal area. And of course, the problem is very it comes from, it's very practical. So say you have a a piece of wire, right? You need to put, so you're on the farm, you have a piece of wire, and then you somehow need to put it in the rectangular shape to optimize the area so that your cows can graze the optimal, the largest amount of grass, right? Or something like that. Or similar problem, then you have a parallelepiped, right, with the sides A, B, and C, and again the surface area is now fixed, right, which is twice AB plus twice AC plus twice BC, right? It has 6 faces, so that's the area, and then you need to find the maximal volume. So that's example, that's first example, that's the second example. And the third example was we talk about perimeter, but not So you have a, so sort of it's the modification of the first problem. So the first problem, you are supposed to draw your, like the shape of the boundary of this object should be a rectangle. Now, so you are allowed to do any curve like this, right? With a fixed length. Length fixed. So the question, so let's say equals to L, and then the question is, what shape will this contour have in order to maximize the area? Like which shape maximizes the area? Okay, so you probably know the answer to the first question and probably know the answer to the third question. With the second question, you need to calculate, right? I don't expect you to do it in your head, but anyhow, so what do you think happens in the first question? What's the, so you are free to vary A and B. You can pick them whatever you like, and then you need to maximize the area. Make it a square. So can you explain it? Of course, like, I mean, it's a simple calculation, but is there any other reasoning apart from that? And then you probably know the answer. So area is A times B, and then we can just solve it from here. So so let's solve it for B. Take derivative of what? So the problem should be formulated like this. You need to find the maximum of this. I mean, if you after already substituted, yeah, okay, good. So right, so B is equal to P over 2 minus A, right? And so the area becomes A times P over 2 minus A, right? And then so now this becomes a function of a single variable A, right? So if you plot the graph, right, it looks like, because now if you take derivative, you can also get a minimum, but you have to right. So and the graph looks like this, right? So this value here, let's find it, right? So the derivative of the function A of A prime is equal to, so this is a quadratic function, right? It's A times P half minus A squared. So A prime is equal to P over 2 minus 2A, and that's equal to 0. So it's this A0, like the optimal value, we can call it A star, is equal to perimeter over 4, right? Which is of course so this is P over 4, this is 0, this is P over 2. Yeah, so if A is P over 4, then B star is also P over 4, so it's P over 2 minus P over 4, which is P over 2, and which is equal to A star. So therefore, indeed, the optimal area when you have both sides equal to each other, equal to a quarter of the perimeter, and the area, this optimal area, kind of A max, is equal to P, what's it? P squared over 16. Yeah, that's right. So this is a like elementary example of an optimization problem, right? So your cows will eat P squared over 16 units of grass and something. Okay, now the problem number 2 may be a bit, I mean, you can see here that, well, what is the volume? What is the volume here? So volume is, of course, what parallelepiped is the product. And, well, as you can imagine, it may not be so convenient to do so, right? Because this area is a function of, it's a quadratic polynomial, right? Volume is a cubic polynomial, and sort of optimizing it may not exactly be the easiest task, right? Although, of course, you probably know what the answer what the answer should look like from some intuition. So we'll address this problem using Lagrange multipliers. But now, what do you think about problem number 3? So if you have a closed, so topologists call it a simple curve, right? So it has no self-intersections. Yeah, so most likely we should think that it should be a circle, right? So can you have a reason why? It should be a circle with circumference L. So what is a circle, right? So how do we, what is so special about the circle? So the circle is, it's a symmetric shape, right? So as we rotate it by any angle, it's symmetric, right? And it's also concave, right? Convex, excuse me. So say you have, so you can kind of make a couple of simple arguments. So first, this shape should be convex. Because see, if you have, say you have a thing like this, right? And the, so of course, like you can almost for free increase the area by reflecting this bulge around like that, right? So if you do this reflection, then of course the area of this shape, which is in this new color, is bigger than the shape of the green thing. So first that so yeah, whenever you have a concavity, you can always reflect it, and that increases the area without changing the perimeter. And second, it should be symmetric with respect to rotations, or center symmetric. So it's sort of it's the same idea, right? So if you have something like, you know, that looks like sort of, you can essentially, you can always act on the, well, what is the, yeah, so if you have something sort of non-symmetric, you can always do another reflection like this, right? So you have some how would I do it? So the okay, I need to remember how this works. But anyhow, so if you have a shape like this, right? So then again, you have to, if this works, like it's so that you should have a center symmetry relative to every axis like that, right? So and it's always easy to make it center symmetric. Again, as in the first part, you can make it center symmetric relative to any axis without increasing the length, right? So, and then if you combine number 1 and number 2 together, you see that the only shape that satisfies 1 and 2 is the circle, right? So once you fix if you fix the length, right? So then the area, which in this case will be what pi L squared over 4, right? So that's the maximal area which you can get, right? So and you can compare it with this, right? So clearly pi over 4 is it's only slightly less than 1, whereas of course it's much bigger than 1/16. Right? So therefore, a circle by far gives you the better area than any rectangle. Okay. So basically, sometimes you can use combination of methods to solve optimization problems. So sometimes it's it's a direct calculation. Sometimes it's some symmetries, right? So and then, but you need to use those symmetries wisely. So of course, they'll help a lot in in our calculations as well. Okay. So now let's address the problem number 2, and in general, how we do optimization of a function, right? So there's a function here of say 3 variables or any other number of variables, and then we need to find its extremum values in the presence of a constraint, right? So an example with a parallelepiped, the constraint was the fixed surface area. So let's consider the another sort of intuitive construction here. Say we have a say you're going hiking, right? And these are the elevation levels, right? As you hike, and then your hiking trail goes like that. So in green you have this. So say f of xy is your function of height, right? So that's the height. And then, well, as it's usually done on maps, like these are just some levels, right? It's equal to some h1, h2, h3, and so on. And then you are hiking on the trail, and this equation, so this line, you can write it as an equation that's called g of xy is equal to k, where k is some constant. Again, so you can think of it as you vary k, there's some kind of level, you have some level function. Right, and then you are asked to find the extremum of f, or extrema, provided that, so in presence of this constraint. G of xy is equal to k, right? So one way to do it would be to, as we did in the first problem with the perimeter, to just solve this and then substitute back. But of course, you understand that it's not always possible even to do, right? So even if G is a polynomial, it is impossible to find the generic solution for polynomials of degree above 4, right? So the quintic degree 5 polynomial, you cannot even write down the solution, and yet alone you cannot do anything if G is some other elementary function, right? Or say sine or cosine of anything. So it's a very there's not much you can do here. So we need to find some other way to do it. Now, so let's see. Let's try to understand how to do this optimization in terms of by studying the vector calculus. So first, let's see what's going on here. So you're walking on a trail. Let's say this is your you're walking this way, right? That's the derivative, that's your velocity vector, right? And then you're coming to, I think this point will be the, at this point, your elevation is the minimum, right? So this looks like there's some slope, and then the trail goes down and then it goes up a bit. So let's try to understand what happens at this point, right? So the gradient of g, right? So your velocity vector. Well, we'll talk about velocity in a second, but yeah. So at this point, so that's right. So basically, the velocity here would be parallel to the gradient of the one second. Oh yeah, there's right. So yeah, velocity goes this way. Now the so we'll see how the height function changes, right? So say f of xy is equal to some, well, let's call it h. H is equal to f of xy, and then the as we discussed that this value of the function changes, so the fastest change goes along the gradient. Along the gradient vector. So nabla f, right? It would be the vector where the this function changes the most, right? And then also the essentially what we need to do, we need to look at the point here where the function g of x comma y is equal to k, where this would intersect. So right. So in other words, we need to find the maximum value of h, where the curve g of x comma y is equal to k intersects, where these two lines intersect. And so to find maximal h such that these two curves, well, this one and this one, intersect, and you can see here that they'll have the common tangent line, right? So if you draw the tangent line as you hike on the trail, it's a tangent, it's a red vector which is tangent to the red curve. Then there's a tangent line to the green level, right? And there's a tangent line let's call this vector tau. So because this curves intersect, you also can see that the velocity vector, the tangent line to red curve, is parallel to the tangent line of the green, and these are also called level curves. Right. So if tangent lines are parallel, it means that we have the theorem that the gradients are also parallel, right? So gradient of f goes this way. So it's orthogonal to the tangent line of the level curve, and the gradient of g is also perpendicular to its tangent line. So because tangent lines are parallel, it follows that the gradients are also parallel. And if gradients are parallel, we can write the following formula so that as vectors, they are proportional to each other. And then I introduced this new parameter, lambda here. So lambda is just the proportionality coefficient, which tells us that it's just a number which rescales gradient vector to the level curve as opposed to the gradient vector to this constraint curve g of x y equals k. So in other words, we need to find the lambda. So we need to find a lambda such that this is true. So in other words, optimization happens at a point. So so f of x y takes the maximum or extremum, takes extremum value. At some point x0, y0, if there exists some real valued lambda such that nabla f of x0, y0 is equal to lambda nabla g of x0, y0, and g of x0, y0 is equal to k. Okay. So that's the condition that we which determines us the position of the extremum. Now, whether it's minimum or maximum, we have to investigate, right? So we need to evaluate functions at all possible values and compare them with the values in the neighborhood and see what's going on here. Okay. Any questions? So the upshot is that we need to compare the level curves or level surfaces if you go to function of more variables, right? So then the tangent lines to level curves are parallel, right? So that determines the position of a maximum or a minimum. And since, as we've shown before, that the gradients are perpendicular to the tangent lines, then it follows that the gradients are also parallel. And the condition of them being parallel can be written like this, where lambda is called the Lagrange multiplier. It's an auxiliary parameter, which we don't need for our problem, but it gives us this system of equations. Sort of, it's part of the set of equations. So essentially, what we're doing here. So see here, let's count the number of equations, the number of unknowns, and so we can rewrite those equations like so. In an example of two dimensions, gradient is a vector whose components are partial derivatives. So we can write it like this: that fx is equal to lambda gx. Fy is equal to lambda gy, and then g is equal to k. Right. So we introduced one new variable, this Lagrange multiplier, but we also have one more equation, which is the constraint. So therefore, if you at least kind of formally count the number of equations versus the number of unknowns, they're equal to each other. Of course, like you cannot count them literally like in linear algebra because these equations are not necessarily linear, but at least it gives you the hope that the constraint makes sense. The solution may not, this problem may not have a solution, right? So there may not be any minimum or maximum, as you know, right? So there are also functions that do not have any minimum or maximum. There are other examples. Yes, so I remind you the gradient vector is so gradient f is fx, fy. So and gradient g is gx, gy. So this first equation is equivalent to these two equations, right? So they come from gradient f is equal to lambda gradient g. Was that the question? Or sure. Now, let me give you yet another way of thinking about this system, right? So instead of, so when we have a function, right? So, okay, so that's another way of thinking. So let's introduce a new function. So let's call it S, which depends on x, y, and lambda, and it's equal to f of x, y. Yes, f of x, y plus lambda times g. Actually, let's put minus here to make things pretty, but it doesn't matter. So g of x, y minus minus k. Oops, what's going on? Okay. So I implemented the constraint by multiplying it by lambda. So question, what was lambda again? Yeah, okay, let's roll back. Maybe I shouldn't go as fast as we do. So yeah, so lambda here, so to understand the statement, sort of the idea about tangent vectors being parallel applied to this picture, right? So if tangent vectors are parallel, then we have a theorem that the gradient vector is perpendicular to the tangent vector. So if gradient vectors are parallel, it means that there is a constant here, right, which we call lambda, and this lambda is the Lagrange multiplier. Which is the proportionality coefficient between these two vectors. We now treat lambda as another variable, right? As a variable which we have in the system of equations. It's it's not directly related to any eigenvalue. That's right. Yes. I mean, I guess you can try. I don't think there's a point to try to represent it as an eigenvalue problem. But what does make sense is this, right? It's instead of considering function f, just f of xy in the presence of the constraint, let's consider this function s, which is the following combination here. Okay, and now we treat lambda as the new variable, right? So we had function of 2 variables, now we have function of 3 variables, and you treat s as an independent function of 3 variable, and the task is now will be to extremize s. Let's see what's going on, right? So extremization would imply that all partial derivatives as x equals to 0. So at least, okay, so so extrema of s will appear, we should look for extrema of s among the, in the locus, which is obtained by extremizing this, right? So the first step would be to find in all the partial derivatives of s and then to put them to 0. So sx is equal to 0, sy is equal to 0, and s lambda is equal to 0. What does this equation give us? It gives us fx minus lambda gx equals 0. This equation gives us fy minus lambda gy equals to 0. And finally, this gives us the constraint g minus lambda is equal to 0. So you can see that this is precisely that system of equations above here. Right. So this S is it's a prototype of the so-called well, it's actually not the prototype. It's a Lagrangian. So it's a Lagrange function. So when you study differential equations or classical mechanics, if you have physics degree, if you need it for the physics classes, you will definitely know a lot what sort of more what it is, right? So it's a kind of a zero-dimensional version. So when you solve a system of when you study, say, mechanics of motion of particles or some bodies, that you would write a function like this for all the degrees of freedom on your system. So here it depends only on coordinates, but your true Lagrange function would depend on velocities also. So it's a function. So let me give you an example. It's a side note. So it's still script L. So if you have sort of x, the derivative. So if x of t is your degree of freedom, it's the coordinate, then the Lagrangian would look like x prime of t squared over 2. And basically that's the kinetic term, but instead of potential term, you put it with a minus sign. So energy is in the kinetic term plus potential term, but the Lagrangian will be kinetic term minus the potential term, minus the potential, which depends on x and on x prime, right? And then you would need to extremize it. You need to write some equations. So what you're actually extremizing is the integral of it. So it's the integral of L of x prime, and t dt over some trajectory, and this is called the action, mechanical action. And extremization of the action would lead you to equations of motion. In particular, you'll get F equals ma this way, right? So F equals ma from here would obtain this mx double prime is equal to negative gradient of potential V, which is, as we discussed a couple of weeks ago, is the force. Yeah. Right. And just that's where the name comes from. The origin here is classical mechanics. So that's what Lagrange himself is famous for. Oh, I'm sorry, it's a typo. It's a typo, yes. Thank you. And that's when you write fast, you make typos like this. Yeah, of course, it's G minus k is equal to 0. Okay, so yeah, so that's the idea. So you elevate lambda to the level of new variable. You treat it on equal footing at the level of this function here. Yeah, and then you just extremize it. So of course, the task will be here to solve. So eventually, what you need to find the value of x0, y0, and the value of the function where it's its minimum or maximum. So you don't really need lambda, so you can sort of get rid of it, right? So, for example, in these two equations, you can easily get rid of lambda. Okay. Good. So let's solve this problem with the volume and the perimeter using this method. Volume of the parallelepiped. So what will be this function s here? So s will depend on 4 variables now, right? That's the volume itself, which is x, y, z, minus lambda times the perimeter. And now let me absorb the perimeter area. Which will be what? xy plus xz plus yz minus little a, and here little a will be the area over 2. And so there's a factor of 2 which I absorbed. Because the area of the parallelepiped is twice the sum of products of its edges, lengths of edges. Okay, so Sx is equal to yz minus lambda y minus lambda z. Sy is equal to xz minus lambda x minus lambda z. As z equals to xy minus lambda x minus lambda y. And finally, you have the constraint, right? So as lambda, which is xy plus xz plus yz minus a. So they're all equal to 0. So this is equal to 0, equal to 0, equal to 0, equal to 0. How did you get that formula? The formula for S? Okay, so the prescription for formula for S would be that, yes, so you write your function. This is your f of x, y, z, the volume function. And then, and this is the constraint. It's g of x, y, z is equal to a. Right? It's same as here. You don't have, so in principle, you don't have to write it. You can immediately proceed to this kind of system of equations, which are here, right? So you don't have to do it. So we already talked about it, right? So that the extremization problem is given by well, it's basically yeah. So let me write it again. So that means that it's the first three equations here are equivalent to gradient f is equal to lambda gradient g, right? And the third equation is the constraint itself. It's g is equal to k, or a in this case. Now, f and g are functions of three variables, therefore there will be three equations. Okay. Sure. Yeah. So now we need to solve this. Well, now, well, as you can see here, it's not particularly easy to do, so we need to come up with some tricks. Right. So one of those tricks would be to so let's focus on the first three equations, right? So then let's multiply the first equation by x. So we have x, y, z is equal to hold on, why do I want this? A second. Okay. Yeah, in the book there's a different problem here. Yeah, so let's say so this x, y, z is equal to, so yeah, I'm taking the first equation, multiplying it by x. X, y, z is equal to lambda x, y plus xz. And similarly, you can multiply every equation by the missing variable, right? So second equation multiply by y. Then you get lambda xy plus yz, and then you multiply it by the third equation multiplied by z. So you get lambda xz plus yz, right? And then you can sort of compare them pairwise, right? So you can say compare first and second. That gives us xy plus xz is equal to xy plus yz, right? So that can remove that. So now we know that none of those variables is equal to 0, right? Because well, otherwise you're not going to have a parallelepiped, right? So of course, like you can put any of those variables to 0, and then it will give you the minimum of the volume, which is 0. So none of the variables is equal to 0. So this concludes that the value is equal to x equals to y. And now we can compare second and third equation. We have xy plus yz is equal to xz plus yz. And that gives you that y is equal to z. And so therefore they're all equal. Right? So x equals to y is equal to z. Right, and yeah. So therefore, from the constraint, we can find what those values are. So it's x squared plus y. Well, it's let's write it again. Yeah, so xy plus xz plus yz is equal to a, and they're all the same. So it's 3x squared is equal to a. So x is equal to root a of 3. Obviously, it's a positive number, and the volume equals z cubed, right? Or because little a is 1/2 of the area, it's area over 6 to the power 3/2. How did you get these two equations below? So what I said here, yeah, so let's, the trick was to take this equation and multiply left and right hand side by x. And then take this equation and then multiply left and right hand side by y. And then take this equation and multiply left and right hand side by z. And now I'm composing these two equations. So see here, the left hand sides are the same for all of the equations. So if I combine first two, I just compare the right hand sides, right? I get the first equation. If I compare, if I take second and third, I'll get this. So notice that lambda did not need lambda here. So it just dropped out. You could find lambda if you want, but you don't need it. So Cameron, does it sound good? Yeah. It was M. Okay, Cameron was explaining. Do we get rid of the negative solution of x because we can only have a positive volume? Yes, that's right. So, if you just formally optimize find the extremum for this function, you'll get more solutions. Yeah. So we only pick the positive branch of the square root because of the the physics constraints, right? It's plus here because of that. Yes, so if you take the negative branch, you'll get that minus v, right, which will formally be the minimum. Yes, this equation is true for every parallelepiped, right? So we took an abstract, any parallelepiped with sides whose edges have lengths x, y, and z. It's absolutely true for every parallelepiped. So if you look at the book, they have a solution where you have like a box, right? So there's a problem here. You can read about this in the book. So like it's an open, right? So like this is field, right? And this is field, but the box is the open. There is no cover, right? So and the problem in the book optimizes the area, the volume of the so the area of this box. So in this case, area is equal to 2xy plus 2yz, and then plus only xy, right? Because the upper side is empty. And then you do the similar calculation, and then you find here that the optimal solution happens when x is equal to y and equals to twice z, right? So it turns out that here, it's interesting. So here we have found that the optimal volume of the parallelepiped with all, with 6 faces, right, is attained when we have a cube, if all the edges have the same length. Whereas if we have a box, then turns out that we get the maximal volume, provided that so z here is the height, right? So xy is the area of the bottom. This is x, this is y, this is z. The maximal volume is attained with the given area is attained when the height is twice less than the edge, than its height. It's kind of intuitively clear, right? So if you don't need to cover the top, you allow it to make it a bit, narrow, like it doesn't have to be as tall. Okay. Let's take a quick break, maybe, and I'll reconvene in like 5 minutes. Okay. Any questions so far? So I just got an email from Emma, our grader, and she said that she'll post the solutions for quiz 3 today. So those of you who are asking the solutions, they'll come soon. Okay, let's look at another problem with constraints. Now, so we have a function f of xy, which is a paraboloid, sort of with this elliptic. So it's a paraboloid, right, with a horizontal cross section would look like an ellipse, right? And then the task would be to find extreme values of f on a circle. On a circle, x squared plus y squared is equal to 1. So here we can set up this action function s of xy lambda, which is equal to ax squared plus by squared minus lambda times x squared plus y squared minus 1. Yes, of course, yeah. And then we'll optimize it. Right, so Sx equals to 2ax minus 2 lambda x. Sy is equal to 2by minus 2 lambda y. And S lambda gives us the constraint, which is x squared plus y squared minus 1. These are all equal to 0. So we need to solve the system of equations. Yeah, so what we have is this, right? We have ax equals lambda x, by is equal to lambda y, and x squared plus y squared is equal to 1. Now, what do you think happens here? So how should we solve this equation? So what are all the solutions? And let's, for simplicity, assume that A is not equal to B. So this is actually it's not a centrally symmetric paraboloid. So what to get from first equation? From first equation, we have either x equals to 0, right, or lambda is equal to a. Now, if x is equal to 0, from the third equation, we have x equals to 0, therefore y is equal to 1. Can you solve the lambda and find the ratio of a to b? Well, ratio of a to b is fixed, right? So say a is equal to 5 and b is equal to 7. So you are not allowed to change that. So we need to find all solutions with fixed values of a and b. So we need to solve for x, y, and lambda, which satisfy these three equations. Right. So the first triple of solutions: a is x equal to 0, y is equal to 0, and lambda is equal to a. Right. Then let's see. That's one thing. So now if lambda is equal to a, excuse me, no, lambda is equal to b. Sorry. We were exploring lambda is equal to, yeah. So okay, let's talk about lambda in a second, right? So here we used if x is equal to 0, right? Then first equation does not fix lambda, right? And then the second, so we can find y from the second equation. So which means y is equal to 1, and then we plug it into the first equation, and that gives us b times 1 is equal to lambda times 1. So therefore, lambda is equal to b. So 0, 1, b is the first triple of solutions, right? So that's one thing. Let's move to the right. Then let's explore what happens when lambda is equal to a. So when lambda is equal to a, then x is not fixed by the first equation. And then we have from the second equation, b times a is equal to a times excuse me, y. B times y multiplied by a times oh no, it's not so easy. Let's rather do the polar coordinates not going to help too much because that's the it's not exact. I mean, you could, but it's not really useful, right? You just need to find although here we have a circle, you lose this rotational symmetry by the first two equations. So if lambda is equal to a, and yeah, so we say lambda is equal to a. Now we look at second equation. In second equation, we have either either y is equal to 0, right, or lambda is equal to b. Okay. So if lambda is equal to a, we cannot already take lambda is equal to b because b is not equal to a. So we have to go with the solution y is equal to 0. And if y is equal to 0, from the third equation, we have x equals to 1. So if x equals to 1, y is equal to 0, and lambda is equal to b, to a, sorry. Okay. So, right. Actually, it's not just one, it's also plus minus 1. So here y is equal to plus minus 1, and here x is equal to plus minus 1. And apparently it looks like there is, right? So I think we exhausted all the possibilities. So first equation gives us this, x equals either 0 or lambda is equal to a. Second equation gives us this, y equals to 0, lambda is equal to b. And then we have exhausted them all, right? So if x is equal to 0, then lambda is equal to b, and y is equal to plus and minus 1. Right, and if lambda is equal to a, then y is equal to 0, and x is equal to plus minus 1. Okay, and now we need to look at So which points give us minima, which points give us maxima? Well, that depends on the sign of A and B, right? So we can just evaluate that, not sign, but the ratio. So let's substitute f of, sorry, somehow it's still in the, yeah, now it's better. So let's plug in the first pair. So f of 0 plus minus 1 is equal to b. Yes, both. So we have, in fact, we have 4 solutions, right? So there are 2 solutions here and two solutions here and 2 solutions here. All 4 solutions satisfy these 3 equations. So you can see here that the count does not work like a linear algebra, right? So you can have, because equations are nonlinear. Roughly speaking, the counting goes like this. So if you have equation of degree n, then it counts as n linear equations. So here you see you have 2 linear equations and 1 quadratic. So you should actually count it as 2. And the fact that we have four solutions is not surprising. So f of 0 plus minus 1 is equal to b, and f of plus minus 1 comma 0 is equal to a. And then depending on who is bigger, right? Yeah. So basically, if b, so let's say b is greater than a, then this will be the maximum, and this will be the minimum, and they swap if b is greater than a. So I think, yeah, let's plot it. It's always nice to draw some pretty pictures. Oops, sorry. I got the plot with 2 somewhere. Sorry, how do I do this? There was this plot with 2. There's another one. Here's another file. Yeah, so say a is equal to 2 and b is equal to 3. And now we need to draw the cylinder. Sort of, it will be the constraint that the x squared plus y squared is equal to 0. Give me a second, I had it somewhere drawn. Oh, here. So we need to do let me the parametric plot. So that will get the cylinder and then the oops. Say like this one would be as 1, 2, and 2, and 1. And then U goes from well, it's not really. I wanted to plot. Why is it so narrow? Let's change plot range. Yeah, so see here, there's a. It looks like a. There's a cylinder that goes through. Then I can make it a bit higher. Yeah, there you go. So the so red is the cylinder, right? It has it depicts you the vertical thread. It's the x squared plus y squared. So the bottom of this, right, is the circle of x squared plus y squared, right? And then you can visualize this extremization problem by looking at the highest point of the intersection of these two surfaces, right? So the green surface is our paraboloid, right? So it's u and v, like x and y, and then we have a is equal to 2 and b is equal to 1. And see here that they intersect over this surface like that, excuse me, the curve like this, right? So it has two maxima. This one and on the other side, and then two minima. There's this one, and then there's one on the other side, and they're clearly symmetric. Yeah, this is how it works. So if you use this is the if you go back to our original interpretation with the hiking trail on the slope, that's exactly what's going on here, right? So in the blue point, if you hike over this intersection curve, then your gradients will be parallel at this point, right? The blue point and yellow point, and the tangent line will be tangent vectors will be parallel as well. Try to make it a bit more exaggerated to see if it's more stuff. If the paraboloid is more elliptical, the difference between minimum and maximum is bigger. Okay, great. And what will happen if a is equal to b? Which point will be minimum, which point will be maximum, or which points? So we can look at the formula in the calculation. What happens when a is equal to b? Right. So we have a spherically symmetric paraboloid, right, and then intersection will be just a circle, right? So all these points will be minimum and maximum at the same time, right? Because they have the same height. Okay. Questions? So okay, we have now let's talk about well, yeah, let's do maybe one more example. So is their answer usually the same, usually some shape and point a curve on some particular plan? What's plane? Well, I mean, it's not always a plane. It could be a surface, as in this example, right? So we had it. So it's really like you should think about it as some intersecting surfaces, right? And then you're looking at the vector, right? So on the surfaces. So this condition here about equality of gradients. If we get back to our original. So in the first picture here, like with the hiking trail, we look at the intersection of curves. In this last picture, we looked at intersection of surfaces, yes, and it was a certain point on the curve which was obtained by intersecting surfaces. But it's an interesting perspective because in a moment we'll turn to several constraints. So instead of having one constraint, you can have several constraints in the same time, and then your interpretation may appear to be helpful. But we'll get there in a minute. So I think I want to do one more example, but one constraint, and then we'll talk about two constraints or more. Oh, I reached on the bottom of the page. Yeah, let's scroll back. So see, the entire week of lectures fits one big page. Yeah. Okay. So another example. So say, so a nice application for those extremization problems is to find shortest distances from points to some shapes. Like, so say you have a sphere given by equation x squared plus y squared plus z squared is equal to, say, 9, right? Or maybe say 4. And then there's a point P with coordinates 3, 1, minus 1. And then we need to find the point on the sphere. Such that the distance is short. This is a point, A. On the sphere such that the distance AP is the shortest. And so what is it? It's the sphere centered at the origin of radius 2. And point P is somewhere at negative z, right? Beyond the sphere, right? So let point A be described by coordinates x, y, and z, which are subject to the constraint, which is the equation of the sphere. And then the distance is equal to, well, some formula, but now instead of So the formula for the distance involves the square root. So square roots are not particularly nice when we do differentiation, right? Because you get 1/2 square root when you take a derivative. Let's not bother with that. So we know that if the distance is maximum or minimum, so is the square of the distance, because the distance is always positive, right? So if square of the distance is the largest, it means that the distance itself is also positive and largest, and same is true for the smallest one. So the square of the distance, this function d squared of x, y, and z is equal to x minus 3 squared plus y minus 1 squared plus z plus 1 squared. Right, so therefore our action function x, y, z looks like d squared. This is function d squared minus lambda times the equation of the sphere minus 4. Yeah. And then Sx will be equal to, so it's derivative of d with respect to d squared with respect to x. So it's 2x minus 3 minus 2 lambda x. Sy is equal to 2 y minus 1 minus 2 lambda y. Sz is equal to 2z plus 1 minus 2 lambda z. And S lambda gives us the equation for the sphere, which is x squared plus y squared plus z squared minus 4. So we have 4 equations, 3 of them linear and 1 quadratic. Okay. So let's rewrite them in more convenient ways. We have x, so we can cancel the 2. We have x times 1 minus lambda is equal to 3. Y times 1 minus lambda is equal to 1. Z times 1 minus lambda is equal to minus 1. Yeah. So let's solve it for we can solve it for x, y, and z. Right, so then for x is equal to 3/1 minus lambda, y is equal to 1 minus lambda, and z is equal to minus 1 minus lambda. And if you substitute this into the last equation, we'll get 9 plus 1 plus 1 is equal to 4 times 1 minus lambda squared. So that's the last equation here. Or, so 1 minus lambda squared is equal to 11/4. So lambda is equal to minus 1 plus or minus square root 11/2. Okay, and now we have 2 solutions, and so you can call them well, x plus minus, right, which is equal to 3. Well, let's do them. Let's not be lazy. Yeah, so we have solution x plus, which is equal to 3 divided by 2 Oh, that's right. Let's write plus minus. That's fine. Yeah, so it's always, yeah, it's 2 minus plus root 11 over 2. Y plus minus is equal to 1 over the same thing, right? 2 minus plus root 11 over 2. And z plus minus is equal to well, minus 1 divided by 2 plus minus plus root 11 over 2. So we have two solutions, and then what do they represent? So why do we have two solutions? Right, because I remind you what we're studying is the sphere, and then there's a point away from the sphere, and then we're measuring distances. Yeah, so minimum and maximum. So minimum would be the point. So if you draw the line like this, so that will be one point, and then it will also intersect the sphere at another point. Right? So let's call this point A, and that's point A prime. And this is P. Now, which choice of sign corresponds to A? Which choice of sign corresponds to A prime? So in other words, let's talk about this one. So shall I put which? So A has which coordinates? X plus Y plus Z plus, or X minus Y minus Z minus? So it has some X, Y, Z. Now which index plus, right? So right, if you take are you sure? So but I think it depends on what you mean. So when I say plus, it's like this plus, right? So if it's a plus here, it's a minus over there. So the distance becomes shorter, right? So the denominator becomes smaller, so the distance becomes larger. So I would say it's the other one. Because root 11 is what? Root 11 is a little bit more than 3, right? And if there's a minus in the denominator, we have still a positive number in the well, okay. I think what we need to do, we need to actually calculate the distance, right? It's kind of hard to yeah. So we need to look at the distance. So you need to plug it into the distance. So lambda is actually equals to. Well, we haven't calculated lambda yet. Yeah, so we didn't do the lambda. So we got rid of lambda. Oh, sorry, like -1. Yeah, so square root 2. Oh, it's 1. I'm sorry. Yeah, thank you. Yes, we made a mistake here. Yes, that's right. So there's 1. Therefore, there actually will be cancellation. Yeah, good point. Otherwise, there's something fishy going on. Yes, thank you. There's a plus sign. Yeah, so there's a plus here. So therefore, x plus minus is equal to 6 divided by well, minus plus root 11. Yes, that's right. So y plus is equal to 2 is 2 divided by minus plus root 11, and minus z is equal to 2 plus minus 2 divided by root 11. Yeah, like this. Right. So for there are 2 points, right? So one is minus 6 over root 11 minus 2 over root 11 and then 2 over root 11, and then another one is 6 over root 11, 2 over root 11, and then minus 2 over root 11. Okay, so now which one is A, which one is A prime? The second is A. Why is that? It's closer to P, and then you looked at the distance function, right? So if you look at the distance functions, we have so if you have a positive number, which is like 6 over root 11, which is a little bit less than 2, right? And then you have that number minus 3, as opposed to here, if you have a negative number, then you have negative 3 minus that number, and the square of that will be bigger. And same true with y coordinate and with z coordinate. So this is A because well, it makes the distance function smaller. So this is A prime. Okay, great. Great. Any questions? Yeah. Here we go. And finally, let's talk about two constraints. Two or more constraints, like several. So yes, so extremization problems with several constraints. So when we had one constraint, so I'm going to explain you the idea using two ways. So first, using this S function, and then using some geometric intuition. So we had when we had one constraint, we had, say, we had a function f of n variables, x1 through xn, and then we had a constraint g of x1 through xn is equal to 0. If it's k, you can actually move this k to the left. It doesn't have to be, you don't have to put this explicitly this way, right? So therefore, we introduced a new function, x1 through xn, comma, lambda, which is f of x1 through xn, minus lambda times g of x1 through xn. Again, I have absorbed the right-hand side of g into the g itself. You can just redefine g like that. And after all, the constant term which we'll have here will be negative lambda times k, or rather positive lambda times k, and it does not. It's a constant, and it does not affect the derivatives, the calculations. And the condition was that the gradient s for optimization, gradient s was equal to 0, which led to the following conditions. So as the partial derivative of x1 is equal to 0, partial derivative of x2 is equal to 0, etc. xn is equal to 0, and s of lambda is equal to 0. So we had a system of n+1 equations with n+1 unknowns, which in general we have hopes to solve, right? And we looked at some examples. Now let's say we have several constraints. Say k over here, m constraints. So you can see that generalization is very straightforward. So the function that we're interested in, f of x1 through xn, and now we have more constraints. We have g1 of x1 through xn is equal to 0, g2 of x1 through xn is equal to 0, etc. gm x1 through xn is equal to 0. Now, examining the above, construction, it's natural to propose the following generalization. So introduce another function s, which now depends on all x's, x1 through xn, and m lambdas, which is equal to, well, you can guess it. So it's f of x1 xn minus lambda 1 times g1 minus etc. minus lambda m times gm. So by doing so, we taking into account each of those constraints at the same time, and then the new condition will be as before. So gradient s is equal to 0, which will lead us to the system of equations sx1 is equal to 0, and so on, sxn is equal to 0, but also s lambda 1 is equal to 0. So these are partial derivatives. S lambda m is equal to 0. So these first equations become so these first equations become fx1 equals lambda 1 running out of indices, right? So the g, okay, we have to, let's say the g1 x1 plus lambda 2 g2 x1, because all of these guys, they depend on x1. We need to differentiate with respect to x1 every function that stands here, and so on, and then plus lambda m gm of x1. That's the first equation, and then so on. And the last equation will be fxn is equal to lambda 1 g1. Well, so it looks like a matrix here, right? So g1 over xn plus lambda 2 g2 derivative of xn, and so on, lambda m gm over xn. Equivalently, you can write these equations as conveniently, we can write them as nabla f is equal to lambda 1 nabla g1 plus and so on plus lambda m nabla gm. Right, and then finally, on the last equations, they just give us constraints, right? So these are derivatives with respect to lambdas, and they give us g1 is equal to 0, etc. gm is equal to 0. So all in all, we have n plus m equations, and also n plus m unknowns. Which hopefully should work. Questions? Let's look at an example when we only have two constraints. So I think, so if you're confused about this, the multitude of equations, the reason, I think the easiest way to understand is to look at this S function, right? So can you move the screen to the right? Yeah, sure. With nablas, right? So yeah, so this is the this formula here. So before we had nabla f equals to lambda nabla g, right? And now we have in the right-hand side, we have a bunch of them. So we have converted like this. So nabla f is equal to sum lambda I nabla gi, and goes from 1 to n. But if you, yeah. So in that, coming back to I think was Shaila's question, the geometric meaning of this equation, right? So remember before we said that the gradient vector of f of the function that we're studying should be parallel to the gradient vector of the constraint. Well, now it's not the case anymore because we have a bunch of constraints. So instead, what should happen is that the gradient of the function is represented as a certain linear combination of gradients of constraints. And now we actually have to find the coefficients in this linear combination in order to successfully complete the extremization problem. Yeah. So in this case, here we actually do need to find those lambdas, otherwise you won't be able to find the exact direction where the gradient of the function, how this gradient of the function is represented as a linear combination of gradients of those constraints. So let's do one quick example. Say you have a function f which is x plus 2y plus 3z, right? So it's a function of 3 variables. And then you need to find its extrema on the intersection of two curves. So g1 is equal to, it's a plane x minus y plus z minus 1, and g2 is equal to circle x squared plus y squared minus 1, the cylinder minus 1 is equal to 0. So these are g's and this is the f, right? So we just need to plug it into the formula, right? So let's write the function s, x, y, z, lambda 1, lambda 2 is equal to x plus 2y plus 3z minus lambda 1 times x minus y plus z minus 1. So you see here, this minus 1 doesn't really matter. You can drop it, right? Because it contributes to a constant. Minus lambda 2, x squared plus y squared minus 1. And again, this minus 1 is also not important. Okay, and then let's write the equations. So Sx is equal to 0 gives us 1 minus lambda 1 minus 2 lambda 2x equals 0. Sy is equal to 2 plus lambda 1 minus 2 lambda 2y equals 0. As z is equal to 3 minus lambda 1 equals 0. There is no z in the third equation. Then s lambda 1 is the constraint. X minus y plus z equals 1. Oh, sorry. Let's be careful. Minus 1 equals 0. And s lambda 2 x squared plus y squared minus 1 is equal to 0. And then we just solve these equations one by one, right? So from this equation, we get lambda 1 is equal to 3. And then we need to solve the first two equations looks like, yeah, so it's 1 minus 3 is minus 2, minus 2 lambda 2x equals to 0. And then 5 minus 2 lambda 2y is equal to 0. So in other words, lambda 2x equals minus 1, and lambda 2y is equal to 5/2. So x is equal to -1 over lambda 2. Y is equal to 5 over 2 lambda 2. And then we can find lambda 2 from this equation. Right, so we get 1 plus 25 quarters is equal to lambda 2 squared. Right, so therefore lambda 2 squared is equal to 29 quarters. And then from this equation we can find z. Right, so z is equal to 1 minus x plus y. So we're running out of time, right? So here you need to substitute the value of x and y in terms of those found values, right? So then lambda 2 squared is equal to 29 quarters. So therefore, lambda 2 is equal to plus and minus square root of 29 divided by 2. And then we need to look at both plus and minuses. Right, so therefore x is equal to have x plus minus equal to minus plus 2 over square root of 29. Y plus minus is equal to 5 plus and minus 5 over square root of 29. And z plus minus is equal to, so from here you need to do the calculation, is equal to, well, if you do it, is equal to 1 plus minus 7 over root of 29. Yeah. Right, and then you just need to evaluate the value f. So you have two values, f plus minus, right, which are f of x plus minus, y plus minus, z plus minus, and you'll see that the sort of after you do it, the calculation, it will be equal to 3 plus and minus square root of 29. Therefore, the f plus will be the maximum, and f minus will be the minimum. Yeah, so the maximum value is 3 plus root 29. The minimum value is 3 minus root 29. Yep. There we go. So as you can see, it can become cumbersome when the number of constraints and degrees of those polynomials go up, but the general strategy should be clear, right? So they all come from this function here. And the geometric meaning of this is that you're looking for linear combinations of gradients of constraints, which would express you the gradient of the function in such a way that the function maximizes. Okay. Yep, that's it for today. So tomorrow we'll have a review. Please bring your questions. And on Thursday, we'll be having a quiz. Sounds good. So thanks for joining. I'll see you tomorrow. Yeah, okay, go ahead. Yes, Thursday is the midterm. No, it will be the full, it will be the midterm for 2 hours, yes. A midterm about the content of the first 4 weeks. Yeah. No, just the midterm. So this week, only the midterm. Do you think you can release some? Yeah, I put them. So look at the announcement. Yeah, so it's in the announcement. Like I put the link to a bunch of practice problems with solutions. go, is it from different professors? Yes, but they use the same book, right? So like so the link to the quiz, to the midterms that I gave you, I think that's will be very close to the style of ours. Yeah, that's fine. Thank you. Great. Anything else? Good, then have enjoy the rest of your day, and we'll meet tomorrow then. Thanks, bye.